Alright, in the previous lecture we have learned why we need an AVL tree, and hopefully everything is clear there. Now in this lecture we will talk about common operations that can be performed on AVL trees. Basically, it's similar to binary search tree. We perform the same operations, which are creation of AVL trees, search for a node in AVL tree, traverse all nodes in AVL tree, insert a node in AVL tree, delete a node from AVL tree, and delete entire AVL tree. So here, first three operations are same as binary search trees that we discussed in our previous section. Now here, I will go through them very quickly, but if you want more detailed information, please refer to binary search tree section. Now the first operation is creation of AVL tree. Now when we are creating an AVL tree, we are just creating an instance of AVL class. So when we are creating an instance of AVL class, it's creating a root node and setting it to null. Now this operation is same as that we did in case of binary search tree. So the time and space complexity for this operation is O1, because in this case we are just creating a root node and setting it to null. So it's not any time and space consuming operation. So that's why creating an AVL tree takes O1 time and space complexity. Now the next operation is traversing of AVL tree. Now we know that when we are traversing through a binary search tree, we have four types of traversals: pre-order traversal, post-order traversal, in-order traversal, and level-order traversal. So in case of AVL tree, we have same traversals over here. So let's quickly recap them here as well. So the first traversal is pre-order traversal. So in case of pre-order traversal, first we are visiting root node, then we are visiting left subtree, then we are visiting right subtree. So we have discussed the details of this traversal in binary search tree section. So here I just want to show you that in case of AVL tree, it's the same. So if we run pre-order traversal for this AVL tree over here, the order will be like this. We are starting from the root node, then we are continuing to the left subtree. So after finishing the left subtree, then we are continuing to the right subtree. So the order of the pre-order traversal in case of this AVL tree over here will be like this. So as you can see, first we are visiting root node, then we are visiting left subtree, then we are visiting right subtree. So this is how pre-order traversal works in case of AVL tree as well. Now the time complexity for this pre-order traversal is ON, because in this case we are visiting all nodes of AVL tree over here, so that's why the time complexity is ON. Now the space complexity is also ON, because in this case when we are creating a method, we are calling pre-order traversal method recursively, so that's why it's inserting the all elements to the stack memory for the next steps, so that's why it takes ON space complexity. Now the next traversal is in-order traversal. In case of in-order traversal, first we are visiting left subtree, then we are visiting root node, then we are visiting right subtree. So in case of this AVL tree over here, if we start to traverse through this AVL tree using in-order traversal, the order will be like this. First we are starting from the left subtree. As you can see, we have started from 20. Then after finishing left subtree's elements, we are continuing to the root node. Then after finishing root node, we are continuing to the right subtree over here. Now this rule over here is applicable for all subtrees over here. So as you can see, for example, if we take this smaller subtree over here, we see that root node is 30, left child is 20, and right child is 40. So here we have started from left child, which is 20, then we went to the 30, which is root node, then we come to the 40, which is right node. So this logic is applicable for all subtrees over here as well. Now here again, the time and space complexity is ON, because here when we are calling in-order traversal, we have to visit all elements of the AVL tree. So this means that if the number of elements in the tree is n, so the time complexity will be ON. So as we said before, here again we are calling this method recursively. So this means that we need to insert all elements to the stack memory. So that's why space complexity is also ON. Now the next traversal is post-order traversal. In case of post-order traversal, first we are visiting left subtree, then the right subtree, then the root node. So this rule over here is applicable for all these subtrees over here as well. So it doesn't matter how many subtree we have in our AVL tree over here, this logic will be applicable for all of them. So if you run for this AVL tree post-order traversal, the order will be like this. So it's going to start from the left subtree. As you can see, starting from left subtree, then it goes to the right child, then root node, then here again after finishing left subtree, it continues to the right child, then the root node. Then after this one, it continues to the right subtree. So here again for this subtree also, the logic is same. First we are visiting left child, then the right child, then the root node. Then at the end we are visiting the root node of this whole AVL tree over here. So in case of AVL tree, the post-order traversal will be like this. So the order will be like this. Now here again, the time complexity is ON, because in this case also we are visiting all elements of the AVL tree, and the space complexity is also ON, because in this case we are calling this method recursively here again. Now the next traversal is level order traversal. Now in case of level order traversal, as we said before, we are visiting elements level by level. First we are starting from the first level, then we are continuing to the second level, then the third level, then the fourth level. So for this AVL tree, if we run level order traversal, the order will be like this. First starting from the first level, then visiting all elements in the second level, then visiting all elements in the third level, then visiting all elements in the fourth level. Now here again, you need to take into account that when we are starting a new level, we are visiting from left to right. So this is how level order traversal works in case of AVL tree. Now here again, the time complexity is On because we have to visit all nodes of AVL tree, and the space complexity is On because when we are creating level order traversal method, we are using queue data structure because here we are enqueuing all elements to this queue data structure, then we are dequeuing them one by one. So this means that we have to enqueue all elements to this queue data structure. So if the number of elements is n, so the space complexity will be On. Now with this, we have finished all traversals in case of AVL tree. So basically they are same as in case of binary search tree. Now the next operation which is same as with the binary search tree is search operation. So here again, this search operation is same as with the binary search trees. So searching for a node starts with comparing the root node. Then based on this comparison, we are continuing to the left or right subtree. So for example, in this case, let's say we want to search for 80 in this AVL tree over here. Now the first thing that we are going to do, we are going to compare 80 with the root node. So the root node is 70. So here we can see that 80 is greater than 70. So it means that we are going to continue to the right subtree. So we can eliminate all elements in the left subtree. So when we continue to the right subtree, we see that the right child is 90. Now here, if we compare 90 with 80, we see that 80 is less than 90. So this means that we can eliminate right child, we can continue to the left child. So in this case, when we continue to the left child, we see that 80 is equal to 80. So this means that 80 exists over here. We have found it in the left child of this 90 over here. Now here, you can easily see that we have found 80 over here in 2 steps. So this means that the time complexity for this operation is all again, because here from the beginning we have eliminated all elements from the left subtree. Now the space complexity is also all again, because here again we are calling our method recursively, but we are calling it only either for left subtree or the right subtree. So that's why the space complexity is all again. Now based on these logics that we discussed over here, let's head over to Java and see how this method implemented in case of AVL tree. Now here we have created our AVL tree class like this. So inside this class, the first thing that we are doing, we are creating a binary node class like this. So inside binary node class, we have a value, height, left and right children. Then inside AVL tree, we have created our constructor like this. Basically what we are doing over here is we are creating first root node with the type of binary node. Then when we are creating an instance of this AVL tree, it's creating a root node and setting it to null over here. Now if we want to create an AVL tree, inside main Java class, we are just going to create an instance of this AVL tree class over here. So it's going to be like this: AVL, new AVL is equal to new AVL. So if I do like this and run our code with this, we have successfully created a new AVL tree over here. Now let's continue to the other methods of AVL tree. Now as we said before, these methods are same as with the binary search tree, so I'm just going to quickly review them. So here the first method is pre-order traversal. So in case of pre-order traversal, the first condition is we are checking that if the node that comes from the parameter is null, we are returning. So basically this is a base condition for our recursive calls. Then the first node that we are visiting is root node. Then after finishing root node, we are continuing to the left subtree, then the right subtree. So it continues like this. So in case of pre-order traversal, we are calling this pre-order method recursively first for left child, then the right child. Now, as I mentioned, this is same as binary search tree. Now, the next method is in-order traversal. So in case of in-order traversal, here again, our base condition is like this. First, we are checking that if the node is null, we are returning. Then we are continuing first visit the left subtree. That's why we are calling in-order traversal method for the left child. Then we are visiting root node. So here we are printing out the value of node. Then we are visiting the right child. So this is how in-order traversal works in case of AVL tree as well. Now the next method is post-order traversal. So in case of post-order traversal, we know that first we are visiting left subtree, then the right subtree, then the root node. So here the base condition is same as for all traversals over here. First we are checking that if the node is equal to null, we are returning. Then if it is not equal to null, we are continuing calling this post-order traversal for left subtree, then the right subtree, then we are printing out the value of node over here. So this is how post-order traversal works in case of AVL tree as well. Now the last traversal is level order traversal. Now basically level order traversal is different than the other traversals because in this case we are visiting all nodes level by level. So this means that we need to create a data structure in which we are going to insert elements and remove the elements. So for these purposes we are using queue data structure over here. So first we are enqueuing the root node, then we are enqueuing all elements level by level and dequeuing the elements level by level. So with this we are visiting all nodes level by level. So for these purposes I have imported over here linked list and queue class over here to use in level of the traversal method over here. Now the next method in case of AVL tree, which is same as with the binary search tree, is search method. Now in case of search method, the first thing that we are going to do, we are checking that if the node that we are receiving as a parameter is equal to null, it means that we have visited the nodes of the AVL tree and we couldn't find this value that we are looking for. So this means that the value not found in this AVL tree. Now the next case is we are checking that if the node's value is equal to the value that we are looking for, it means that the value exists in this AVL tree. Otherwise, based on the comparison between the value and the node value that we are receiving with the parameter, we are continuing to the left or right subtree. So in this case, we are checking that if the value that we are looking for is less than the node value, it means that we are going to continue to the left subtree. So that's why we are calling search method recursively for the left subtree. Otherwise, we are continuing to the right subtree. So that's why here we are calling search method for right subtree. So in case of search method, the time complexity is all again and the space complexity is all again in AVL tree. Now with this, we have performed common operations on AVL tree which are same as binary search tree. So here in this lecture, I just quickly reviewed them to show you how they are working in case of AVL tree as well. Now the main difference between AVL tree and binary search tree come in case of insertion and deletion methods in AVL tree. Because when we are deleting and inserting elements to AVL tree, if our tree becomes disbalanced, we are doing rotations to make our tree balanced. So with this, we have come to the end of this lecture. So hopefully everything is clear about this lecture over here. So see you in the next lecture.